Hello everybody, I'm Mohsen Imani, an assistant professor in the Department of Computer Science at UC Irvine. This is my pleasure to present our work in Macro 2020. So this work is about clustering algorithms. So clusterings are one of the most popular learning methods analyzing unlabeled data. So these algorithms have application in machine learning, pattern recognition, image analysis, computer graphics, and so on. So to give you an introduction about clustering, these algorithms are naturally grouping objects. So however, clustering is subjective and there is no golden result for that. For example, the following characters can be clustered in terms of their family or employee or in terms of their gender. So there are two general methods for clustering. One is hierarchical and the other one is partitional. So regardless of algorithm, clustering algorithms consist of two main operations. First is pairwise computation of data points and finding the data that they have a closest similarity. Second step is merging the closest data that we have actually find it and updating the cluster centers based on the relative distance of the merged data point. So the pairwise distance computing is based on extensive search among data points in the data, while the cluster update is mostly using arithmetic operation to update and merge the selected centers. So although we are designing a platform which is general and programmable and can accelerate most general clustering algorithms. So in this presentation, I will explain the functionality of our approach over hierarchical clustering. So this is most popular, kind of one of the most popular clustering methods. So these algorithms like hierarchical clusterings are, as you can see on this graph, they consist of multiple steps. So they are operating on original data. They compute the pairwise distance similarity of all data points on original space. They create a distance matrix between all 2x2 data points. Then they cluster data with the highest similarity and merge them together. And then they update the relative distance of all other data points to the newly merged data points. So this method continues until finding a tree-based hierarchy based on the number of levels that we want. So as I said before, the pairwise distance computing are the main computational cost of clustering algorithms. So over original data, we often need to use a complex distance metrics such as Euclidean distance for computation. So however, these metrics are not hardware friendly, specifically for PIM architecture. And from other hand, existing PIM technology have several reliability issues. And this makes the existing binary representation, like original data, very sensitive to possible noise in hardware, specifically if that happen on like exponential or significant bits. So our solution is to map data point into another space that values can be represented using holographic representation. So the mapping has several advantages. It maps data to a high dimensional binary space that all bits have the same impact on a computation. In fact, there is no most significant bit or least significant bit here. So clustering can happen significantly robust, while we may lose some of the dimension because of the hardware failure, which often happen because of the noise on existing hardware. Also, this mapping or encoding mathematically map data point to another space that the similarity metric can be preserved using simple Hamming distance computing. So rather than using complex similarity metric that cannot be supported by existing like emerging hardware like processing in memory. So here I briefly talk about the encoding module. So that maps data into high dimensional space. So the encoder is based on the idea of hyperdimensional computing. It has been also inspired by RBF kernels that use Gaussian random projection to map data points into high dimensional space. So the result of projection, as you can see here, it mapped to a nonlinear activation function, and after that it binarized in order to have to compute everything in a binary space, high dimensional space, which gives us both robustness and also it gives us a simple similarity metric. So more detailed mathematicals are explained in a paper, so you can refer to that. So let's move on to the hardware part of that. So if I revisit the clustering algorithms into a space that is more hardware friendly, specifically based on emerging hardware, they're mostly bitwise operation, how I can accelerate it on hardware. So clustering algorithms are generally running over large scale data. So specifically because these data points, they do not have label for clustering, we often have a really huge amount of data which are generated and they need to be processed in a reasonable time. So, but we know that when we are running big data, like over the big data, we have several issues in terms of data movement issue. So in fact, the computation by itself, if I compute on CPU or GPU, it is not a main computation cost for me. Now data movement between memory and computing, it is a major cost which dominate the entire energy and execution time. So there are multiple solutions to address that. So one popular method is near data computing that locates 3D high bandwidth memory at the top of the CMOS logic. Although this approach improves memory access latency, the computing and memory units are still two different kind of units here. So data movement can be still a major issue here. The second popular approach is about analog-based processing in memory. This approach supports vector matrix multiplication in a fast analog way. So, however, this approach uses ADC-DAC block to transfer data to analog space, which are actually, they are on a scalable mixed signal circuit, which are taking majority of the chip area. Also, these kind of architecture, they cannot support search-based operations or distance computing that we really ultimately need to be significantly efficient, like Hamming computing or so on. So what we have proposed during last few years, like in the research community, and there's a lot of other work too, our focus was mostly on emerging non-volatile memory, is about digital-based processing in memory. So in our ISCA 2019 paper, like float beam, we show how this architecture, we can support vector-based computation in non-volatile memory with no data movement or data transfer to analog space. So float beam does not support search or distance computing, which are main crucial operation for clustering algorithms. Also, it has been dedicated for acceleration of deep learning. But the operations we really need here to do clustering, they are really different. So here I want to show how we can have a new, like a good architecture, which is programmable and general, and it can accelerate a wide range of clustering algorithm inherently in memory. So this is a general architecture of like dual, which is our digital-based processing in memory. So we have like a storage class memory consisting of multiple memory block. So every memory block that you can see here, it has 1K by 1K size, for example, and it can support tensor-based computing. What does it mean? If you support two columns of memory, A and B, I can write A nor B on the third column. Or I can write so like this actually NOR operation happens internally in memory by selecting two columns, connecting them to VDD and connecting the output to 0. So we name it actually like magic operation. It's based on literature. And if we can support NOR-based operation, we can extend NOR to perform arithmetic operation. We can do A plus B, or even we can do A times B in memory by sequentially performing NOR-based operation. So, but if I can do these operations on a digital data without transferring them to analog space, now I can operate over, I can actually perform a highly scalable solution which can work with no data movement, with high parallelism, and also it can eliminate the necessity of using ADC-DAC block to map data to another space. So it would be a really dense and parallel solution. Simply saying, every memory block here that you can see, like this is this memory, it can support 1K, 1000 operation in parallel. So 4 of these memory block is your GPU. So in storage class memory, I have 10,000 of these blocks. So ideally, I can do 10 million operation if my values are in a good place in memory. But arithmetic operations are not the only operation we need for clustering. We have shown in a paper a new circuit that how we can, with minor modification in memory block, we can support exact search, and more importantly, we can support Hamming computing. So if you have multiple memory rows, I can perform the search operation between a query and every row, and I can tell you how many Hamming distance between a query and every row exists in a row parallel way with single search operation. Also, I can support nearest search operation, nearest Hamming distance search operation, which are key operation in order to accelerate any clustering algorithm. So let me see how we can use it in order to perform clustering algorithms. So here I don't show how we encode the data. The encoding is based on vector matrix multiplier that can simply supported using our arithmetic computation. Now I directly go to the clustering part. So now take a look at here how we can support clustering fully in memory. So the first step of clustering is to compute the pairwise distance computing over all data points. So our solution supports row parallel Hamming distance computing entirely in memory. So by searching for a similarity of A1 to all data points in a memory data block that you can see on the left here on the left, we can compute the relative distance. So if we do it for A2 until AN, we can create a distance matrix completely. So this is a significant cost in order to do it on original space, because data points are usually in a really large scale. But now in memory, we can perform a highly parallel search operation, and we can perform and create this distance matrix in a really hardware friendly way. And this is a major computation of all clustering algorithms. Now, after finding actually the distance matrix, the goal is to find what are the two closest kind of data points together. So we can simply perform search-based operation in memory, and we find in this distance matrix what is the minimum value. So after finding that index, we can refer to the sum S corresponding to every data point A1 to AN. And then based on the index of I and J that we find they are closest, we can use Si and Sj, which can be S2 and S3 here. In row parallel way, we write it in a memory. Then we use this approach in order to compute the Ward coefficients. So just here, in order to clarify, so don't be confused, this part is highly depends on algorithm. Like here, I'm using clustering algorithm with the Ward coefficient. So Ward coefficient is relatively kind of expensive, and because of that, we need to perform the search-based operation. So we need to actually perform arithmetic operation between S vectors in order to compute some coefficient. But as you can see here, everything I do, it's vector-based operation, which can be supported using our arithmetic operation. This addition, it shows pin-based addition that we can perform between first column and this column and so on in order to compute the result. Then similarly, we show how we can do division in memory. So based on some division, we can compute the Ward coefficients. And after finding that one, we refer to the distance between AI and AJ, one of these columns that it shows the distance of between two closest value that it has been selected. For example, if A1 and A2, they become the closest one, we will refer to the second column. And after that, what we do, we multiply the Ward matrix, the coefficients, with this distance, relative distance values in order to find the distance of every data point with the merged AI and AJ. There are two data points that it has been selected in order to be merged. So this is the algorithmic part, so I'm not going through that. But what I wanted to show, everything can happen now based on vector-based operation and search-based operation in memory. And we have a very clear data flow that it can support any clustering algorithm. Let me show you in more details or high level how it can happen in memory. So if you look at here, we show the layout of memory at the bottom to show how this computation can happen entirely in one or few memory blocks that they store the values. So if I have encoded values stored in a memory, so we create a distance matrix, then we compute the nearest data, then we compute the Ward coefficients based on some addition, division that I explained, and finally we update the relative distance. And you can see all these computations are vector-based operation. And finally, we need actually to just update the relative distance, as I mentioned before. And we need some reserved memory in order to do these computation too, because if I want to do arithmetic operation, addition, multiplication, division, I need some reserved memory to do intermediate result of computation, because I'm based on NOR-based computation. So in terms of data movement, we have some, we actually provide some infrastructure that it can support internal data movement in memory. So as you can see, if I want to transfer data between one block to another block, I don't have network on chip in memory. So what I do, we actually use some interconnects, very lightweight interconnects that connect all the memories in memory blocks that they are in a single row of a block, a bank kind of. And what we do, these memory blocks, they can transfer bit serial, row parallel data transfer between each other. Also, if I want to have more complex, I can say data movement, we are actually proposing some mechanism that this data movement can happen in a very lightweight in a memory. So this is very crucial for us in order to get advantage from this architecture. So this is a general structure of our architecture consisting of 64 tiles, 256 blocks per tile, and also 1K by 1K memory size. So our approach is from kind of device up to the application. So we do some circuit simulation, then we give it to the architecture, cycle accurate simulator we design, and we connect it to the applications like scikit-learn in order to directly run clustering algorithm in our architecture and emulate the functionality of dual, which is our architecture. So this is the specification of our like processor tool, like chip 2, which I'm not going to the details of that. So in terms of quality of clustering, we are providing comparable accuracy to the baseline. So of course, our accuracy depends on our dimension, but we show if we go to like 4,000 dimension, we relatively get a good result. So of course, this dimension can be estimated by mathematics that we have for the encoder. And also we compare our approach with the state-of-the-art high dimensional clustering approach like LSH, low quality sensitive hashing. But as you can see here, clearly we are providing higher quality of clustering and also provide maximum quality in much lower dimension, which means more efficiency. And this can happen because our encoding is nonlinear. So I should mention that the cost of our encoder is more than LSH and other existing encoding method, but encoding has a single time cost. So it's not a major part of that. But similarity search and other computations are happening iteratively over the data. So now in terms of efficiency as compared to the GPU, it's a kind of best result we can get. We can be on average about 60 times faster and 250 times more energy efficient than GPU. And this efficiency comes because parallelism that can be that dual has, our architecture has, that can be supported by ensuring data availability, because our data is on a memory in a good location. And second, addressing data movement, because now we do computation in memory without moving it to the processors. Also, we show the impact of different parameters. So if I don't have Hamming computing circuit, what is going to happen? We show that we are even slower than GPU. So it's really crucial to map data to high dimensional space and do Hamming computing in a parallel way in memory. Also, we show the impact of interconnects are important, but not really crucial. So if we don't use it, we can have like 4 times the slower computation in dual if we don't have any mechanism to address data movement in memory. But in summary, our digital-based processing in memory has several applications beyond existing machine learning method. So for example, they can be used in order to accelerate bioinformatic application, database, graph processing, and so on. So all these algorithms are using tensor-based computing, which can be perfectly mapped to the memory operation that we have. So I would like to conclude my talk. Thank you so much for your attention, and feel free to send me email if you have any question.